welcome to the keynote address for SmartFriends U, Languages and Libraries. Our keynote speaker today is the creator of the Standard Template Library. And as an illustration of how fundamentally innovative this library is, I want to tell you about how one programmer experienced this library. My first encounter with STL was when I was working as a C++ contractor, and so I would work for several months on a particular project with a particular framework and a set of container classes, and then I'd move to another project with another framework and another set of container classes. And when I heard about this library becoming part of the standard, I was very excited because, of course, that meant that now I would have a single set of container classes. As I went from project to project, it would always be available. So I got all the books I could on STL. The very first books tended to not be very good, but we have a better assortment back there, so you can peruse those. Yeah, that's right. I found out that it was difficult to learn about this set of container classes because the syntax was very different than previous container classes that I worked with. I had one advantage because there was the source code, but the disadvantage was that reading the source code didn't really seem to help you understand how to use the classes. The other problem seemed to be that when I read about the STL, all of the books and articles all seemed to be backwards. Because instead of talking about the container classes, which was the really important thing, because that's what I wanted to know about, they talked about things like iterators and generic algorithms and things like that, which didn't really seem that important to me. So, but one of the things that I did read about was that Alex was very interested in generic algorithms. So I said, well, let me look and see what goodies we have in this set of generic algorithms. And it's like, wow, we have sort. That's really cool. And we have find and count. You know, these don't really seem all that special. I mean, we've all written these several times. And that's, of course, when it finally dawned on me, yeah, we've all written these several times, and that's really stupid. We shouldn't be writing these over and over again. We should write these once. And that is when, you know, the penny dropped, the application launched, the light bulb came on, whatever the right cliche is, it finally dawned on me what was really special about this set of libraries. It wasn't just that we could now operate on any type. In order to operate in any type, we need to have templates, but other libraries were using templates. That wasn't special. What was special was the concept that if we created iterators that modeled certain concepts of behavior, then we could make algorithms that would work over any type of container and any kind of range or selection of objects. And this was innovative, and this was exciting. And so I want to tell you a quick story about, I don't know how much truth there is to this. Alex can tell us how much truth there is, but this is the way I heard it, so it's the way I'm going to tell you. Andrew Koenig was the chair of the C++ Standard Committee as it was about to release its first standard. And he called Alex and said, are you going to propose your library as part of the standard? And Alex said, well, the standard's almost finished. This is a big library. They're not going to accept this. It's too late in the cycle. They're ready to ship. And Andrew said, you're absolutely right. They won't accept it if you don't propose it. So Alex and his team went without sleep for several weeks as they pulled together the proposal to make this part of the standard. And when they brought it to the committee, his prediction was absolutely right. The committee said, we're way too late in the cycle. This is way too big a proposal. Look at this. Wow, this is pretty good stuff. We really need this. So I think that the real mark of the quality and value of STL is not that it's in the standard. Because if you look closely at the standard, you'll see warts and wrinkles. It's not all poetry in the standard. The value, I should say the mark of its value, is that it was accepted under the most favorable circumstances. Under the least favorable circumstances, right. Because the committee had already done a good job. Without the STL, the C++ standard would still have been something to be proud of. It embraced current practice, but extended it, and all sorts of new ideas to take C++ to the next level. Without this library, it still would have been a remarkable achievement. And users weren't asking for this. As typified by me, we didn't know what it was about. But the committee had the vision and recognized the genius of what the library was. And so that's why I think that we can look at the library and say it's truly remarkable, not just because it's in the standard, but because it was accepted when it was really against all odds to be accepted. So anyway, I want to ask you to extend our welcome to our keynote speaker today, our friend, Alex Stepanov.
Thank you very much. It was a very generous introduction. And the story was almost exactly true, except Andy Koenig did not call me. He sent me email. This talk is not about STL. I'm not going to mention STL. And in some sense, there is a reason. Is it all right if I try not to use the microphone? Or, no, we're recording. STL is a part of C++, and it's a useful thing, maybe, I don't know. I have my doubts. But fundamentally, it is a result of trying sort of to figure out what programming is about. And the fundamental idea behind STL is that actually programming is based on some very fundamental truth, that it's not just hacking, that it's not just doing some practical, useful things, but it reflects something of as fundamental nature as Maxwell equations. It's a very tall order, what I'm saying, but at least that's what I believe. And it's very hard to explain. So a while back, in 1999, I got a little prize from a small engineering school in upstate New York, Rensselaer Polytechnic, which asked me to give a university lecture addressing all kinds of undergraduates and explain to them what my opinion on programming, generic programming in particular, is. And I started thinking about it and decided that the only way to explain what it is about is to tell them the history. History is a good way of sort of teaching how things evolve. And, well, the term generic programming was introduced in 1988 by Dave Master and me in a paper. So I said, is it where I need to start? I said, nah. I mean, I actually stole most of the ideas from some other people. So I was going back, and eventually I ended up very far back. I ended up in roughly 6th century BC. And that's where the story starts. I'm not really making it up. Fundamentally, and this is very sad that nobody remembers it. It is forgotten over the last 150 years. If you ask Leibniz, who invented mathematics, he would know. If you ask Gauss, who invented mathematics, he would know. But then things sort of disappeared. Nobody remembers. Mathematicians do not know who invented mathematics. But there is a person who started it all. And the person of whom you heard, but you do not quite probably comprehend the significance of his contribution, is this guy. This is his photograph. Again, sort of part of the problem is that 19th century historians, especially German historians, went into this hypercritical mode, and they started saying that nobody ever existed, and whomever existed didn't do anything. And therefore, Pythagoras, whatever we knew about him, was not valid anymore because we do not have any immediate sources. I mean, newspapers all rotted, right? So most evidence is at least 150 years after his death. So, but it's very clear that this is the man who started it all. Rather unusual man, was born on a beautiful island in Aegean Sea called Samos, and that's a fact. Why do we know that it's a fact? Because nobody ever challenged that. In case of Homer, every city in Greece would claim to be the birthplace of Homer. Therefore, we do not know where he's born. But even Athens never claimed that Pythagoras was born there. He was clearly born in Samos. We know it about him. And he left after about 20 years, when he was a young man, he decided he has to go to the East and find wisdom. It's this marvelous idea that you have to go someplace and find wisdom. First of all, that you don't have it, somebody else in a foreign country, among the barbarians, might have it. We do not have his itinerary any longer, it's gone, but we could surmise fairly well where he went, if we are not going to be hypercritical, but if we look at what he brought back. So one thing which he brought back when he came back, he decided to start an ashram. He didn't call it an ashram, he called it a brotherhood. But he said, let us all live together in celibacy, not eat animals, because they could be our grandmothers. Transmigration of cells, And let us do good. This is a fairly typical ashram. They have now things like that in India. So it's very clear to me that he traveled to India because no other country had these ideas. Greeks always ate meat, right? Even now, try to talk about being a vegetarian to real Greeks. They do not understand, right? So he brings this new idea, but it's not just an ashram. Because in his ashram, he says, let us also study these things. Ma tema, these things. This is where the word mathematics comes from. This was a rather unusual ashram. The idea was that you don't just do mystagogy there. You do what nowadays we would call science. We do what nowadays we'll call mathematics. So what did he learn? Again, it's very clear that if he got to India, he had to cross some places. There is no direct flight, or at least there was no direct flight from Samos to India at that time. So where did he go? He had to cross through Babylon. This is Iraq, you might have heard, right? And that was just before, probably, Babylon was bombed. It gets bombed every 500 years. At that time, it was bombed by Persians, but not just yet. So he went there just before Persian invasion, and Babylon was probably the most advanced mathematical not in the sense Pythagoras later put to this term, but in terms of arithmetic. They knew more arithmetic, they knew more about numbers than anybody else in the world. And very likely, he's seen something like that. This is Plimpton 3-2, one of the most important things in history of mathematics. I'm sure that you could read it fluently. And what it contains a marvelous list. It contains a list of numbers, which nowadays we call Pythagorean triples. Things like 3, 4, 5. Why is 3, 4, 5 such a special set of numbers? Because 3 square plus 4 square is equal 5 square. So these are triangles which have, if you numbers, sides expressible in terms of whole numbers, Pythagorean triples. So you see this connection with what later becomes Pythagoras' theorem. So he brings some knowledge of numerical methods from Babylonians, and they were quite wonderful. They were able to compute long lists and rather interesting lists. I cannot go into details, but this is not a random list. It's a very clever list because it corresponds with the ordering of Pythagorean triples, sort of when you go on unit circle. And well, for those who are interested, I'll be happy to explain later. So when Pythagoras sort of comes back, he starts this I do not know. Okay. He starts this ashram where he develops this way of studying things. Let's study astronomy, look at the stars, geometry. We will map the movement of the planets to some geometric principles. We'll express them through numbers. And then we will express numbers in terms of music. One of the great contributions of Pythagoras to human civilization is the fact that he invented the musical scale. He discovered that the octave has a ratio 1.5, that the perfect fourth and the perfect fifth is correspondingly 2/3 and 3/4 ratio of the string. The chord, the major chord of an octave. So he found out that music was mathematically based. Of course, his disciples, who thought he was to be semi-divine figure, believed that he was able to hear music of the spheres. And when the stars went up there, they generated these numbers, and he could hear this eternal music. I don't know about that. But in any case, he developed this program of study, which is quite marvelous, even by modern standards. I would join an ashram based on this, celibacy or not. It's not bad if you think about it. And what he came up with, which was this fundamental intuition, the intuition which is way more important than just about any other intuition in science, is the fact, and this is fairly certain that he did say that everything is expressible in terms of numbers. You say, well, we know that. Yes, you know it now in the 21st century, but nobody knew that. The fact that you could describe reality in terms of numbers was a fundamental breakthrough. Probably the most fundamental breakthrough ever. And therefore, along this program, what they decided, they will sort of study the stars, describe their movements, and then describe all the geometric shapes with the help of whole numbers. Because these are the only numbers Greeks had. These are only serious numbers, ints, doubles, they're bad. So the idea was that you need to map geometry into number theory. You have to find, if you like, a quantum of space, this little dot, and then out of dots you will build all the shapes by putting whole numbers of them. And the great tragic surprise, which either Pythagoras or his immediate disciples discovered, there are arguments, we do not know who really discovered that, but Greeks actually believed that he personally discovered it. He discovered the fact that you cannot do that this program is not realizable. You cannot describe geometry with the help of integers. You do need doubles, as we discovered later. And he proved it. It is one of the great accomplishments of the early Pythagorean mathematics was the proof that you cannot arithmetize geometry. Let us see what it means. This is going to be the only proof during this talk, but bear with me. Right? I'm going to do a high school level proof, which is sadly enough not known any longer. For one reason is that it is my reconstruction of the original proof. It was lost fairly early on by the early 4th century BC. They used simple, uninteresting arithmetic proof that such a thing is not doable. But their original geometrical proof, which I'm going to present, is so much more instructive. This is not my original reconstruction. I mean, many other people looked at it, and it's sort of probably how the original Pythagorean proof went. So in order to construct this quantum of space, if you could, then you would be able to find a greatest common measure of any two line segments, right? If everything is expressible in terms of micron, micron will be the universal measure. Everything is measurable in terms of micron. Now we're going to prove that such measure, micron, does not exist. This does not exist in terms of geometry. It's a sad reality, but true. And they realized that if two things have a common measure, they could find it by writing this C code. Right? And you don't even need C++. You say that if two segments have the same measure, then either if they're equal, then you return A. A could measure both. Right? If they're not equal and A is bigger, then you subtract B from A and go down recursively. So you go, and otherwise you subtract A from B, and you go down and down and down and down. So will it ever stop? Did they discover an algorithm? Sometimes it will stop, clearly, right? If we give 1 foot and 2 feet line segments, it will stop after one iteration. But often it will not. So how do you prove it? And that's how they proved it. Let us assume that such a measure exists. And then this measure could measure, both a side of some square and its diagonal, right? There will be a whole number of microns in both things. So if it is a whole number, we could take the smallest square like that. This is a very fundamental principle Greek discovered. This is actually equivalent principle to mathematical induction, that every set of integers, of positive integers, contains the smallest element. It sounds self-evident now, but again, it was a major sort of universal discovery. So they said, if there are many squares like that, let us take the smallest. Okay? We take the smallest square. Now let us see what we could do. This is the square, so there are so many microns in BC, and again, so many microns in AB. Whole number in integer, unsigned integer. Right? So then let us do the following thing. Let us find a point F which is such that AF is equal to BC. Could we do that? Yes, we can, because diagonal is greater than the square. Well, in order to do this proof, they of course had to construct the entire geometry. The geometry was constructed, if believe it or not, to do this very proof. Sort of they came up with the action. So yes, you could find point F. So now let us put a perpendicular from F to some point E, right? It's very easy to see that FC is equal to FE. Why? Because the angle FCE is 45 degrees, right? Therefore, angle CEF is 45 degrees. Therefore, they're equal angles. Therefore, the corresponding sides are equal, right? So we're constructing another square. Obviously, FC is also measurable in microns. Do you agree with that? Yes, because side was measurable, diagonal was measurable, therefore their difference is measurable. The difference of two whole numbers is a whole number in modern speak. Yes? So we just construct this square. Now, if we could only show then EC is measurable in microns, we will be done. Do you understand why? Because then we will get a smaller square than the square with which we started. And that is bad, because we assumed that the original square was the smallest such square. Again, a great insight. This is this argument which appears again and again and again through history of mathematics, but Greek discovered it very early on. Right? So let us look now whether we could show it. And yes, we can. So let us look at, let's construct BF. It's, again, fairly self-evident, actually absolutely self-evident, that BFA, the angle BFA, is equal to the angle FBA. Why? Because corresponding sides are equal by the construction. AF is equal to AB. That's how we put, right? Therefore, the angle EFB is equal to the angle EBF. Why? Because it's 90 degrees minus equal angles. Right? Therefore, FE is equal to EB. Right? Now, we already know that FE is measurable in microns. Therefore, EB is measurable in microns. Therefore, EC is measurable in microns because it's the difference. Okay? Contradiction. This is geometrical proof of irrationality of square root of 2 in modern parlance. Of course, they didn't know these words. They knew just this fact that a side of the square and its diagonal cannot have a common measure. That's how they would say it. But fundamentally, they discovered irrationals, what we would call it now. And it was legendary sort of thing, caused horrendous intellectual crisis in Greek world. There are all kinds of myths. One of the great myths is that, of course, that was a secret teaching. All Pythagorean mathematics was a secret inside the ashram. You were not supposed to disclose this wonderful stuff to unwashed masses. And the person who did was either drowned or drowned in a storm, or something terrible happened to him as a punishment from gods for his sort of terrible deed. It's a very late story, but it was very clear that it was something, tremendous, that the fact that the world is irrational, you cannot reduce it to integers, had these dramatic consequences of the worldview of the Greeks. So again, we end up roughly in the 500 BC, maybe 480 BC. There is a secret ashram in Grecia Mania. All the ashram, Pythagoras, when he came back to Mediterranean, didn't settle in Greece. He went to southern Italy, the part which is called Great Greece, Grecia Mania, Calabria nowadays. And that's where he started his ashram. And Pythagoreans did very well, established several governments, but eventually were overthrown, and the teaching still was secret. We need to wait about 100 years for somebody else. And somebody else is this guy, Plato. There's another guy who is absolutely fundamental for the development of mathematics. And you probably heard more of Plato than you heard of Pythagoras. But for those of you who forgot what you learned, quick reminder, he was a young man, disciple of Socrates, great philosopher who, in reward for his educational effort, was asked to drink poison by Athenian democracy. And Plato was very disappointed. His beloved master died. I mean, this sort of amazing thing that the wisest person on earth, the most generous person on earth, was killed. So Plato leaves Athens, which he loved dearly. He was also about 23, 24 years old, I would think, and goes abroad, first to Egypt, where he studies whatever we do not know, and then he goes to Sicily in Grecia Mania, Calabria, where he meets Pythagoreans. He studies with them, learns mathematics very well, and goes back to Athens and starts the first university. Okay? That is, he goes into a small garden outside of Athens, which was dedicated, this garden, to an ancient hero by the name of Academos. Therefore, they called the garden Academia. So that was the first university. He said that we will start studying, and it's going to be open university, free university, very progressive idea. We'll not charge tuition. And what are we going to study? That's what he wrote on the entrance to the university. Agiometreos meideis eizito. I'm sure you understood. That's what it means in English. If you don't know mathematics, don't enter. Sort of the the presupposition of Platonic academy was that you should not attempt any studies till you spent about 8 years studying mathematics. And they had very advanced program. And there is a marvelous book by David Fowler, which attempts to reconstruct mathematics of Platonic academy. That's its title, Mathematics of Platonic Academy. And it's quite clear that what they were studying was extremely advanced, even by modern standards. If you look at the book, yes?
Where would you study the precursor mathematics? Was that available, like?
No. I mean, that was, you would study there, right in the academy. Academy would lecture on mathematics for 8 years.
So
and
like
then you,
yes.
So after that, after 8 years of math, they would let you study political science. I think it would be a fabulous thing. Imagine how nice it would be to live here if every politician went through 8 years of heavy mathematics. They do fuzzy math. Yes, that's the letters now. So, extremely progressive establishment. It was freely available to everybody, even to slaves and, I could not even say it, to women. Yes, women were encouraged to study mathematics. Plato was thousands of years ahead of his time, and he thought that there should be educational equality and women should study as much as men. Well, he even attempted to convince his Athenian compatriots, everybody, that everybody should study mathematics. And once he declared a public lecture, something like that, he said, "Come and I'll tell you what is good." The lecture was entitled On Good. And people came in large masses because they were sure he is going to talk about investments. I'm not making it up. You say, Alex is making it up, he's joking. No, we have a fairly contemporary account. They thought he's going to peddle either how to invest or how to get big muscles or something like that. And instead of that, he told them to study mathematics. They wouldn't let him finish. So, there are some problems, even in the most enlightened societies. Again, do not misunderstand me. Athens of that time was probably the most wonderful society in terms of its intellectual exuberance, But, well, they wouldn't listen. So, the wonderful thing which happened is that eventually they developed a curriculum which, after a certain point, was put in a book. I'm going to skip some great contributions by Plato and go another 100 years to Euclid. This is 2 instead of 3. I don't know why it says 3. Somebody forged it, Sean. The numbers go sort of backwards. In those times, they were counting backwards. So, yeah. Yes. So, we know very little about Euclid. Actually, we know less about Euclid than we know about either Pythagoras or much, much less than Plato. Plato we know a lot. But this is the man who wrote the most famous book in mathematics, Euclid's Elements, which for so many years remained the standard math textbook throughout the world. And the book which had tremendous effect on sort of development of Western civilization until very recently was sort of used as a book with which one should form his or her mind. Sort of canonical example is the greatest American president. Whom could I mean? It isn't Bush probably, is it? So it's Abraham Lincoln. When Lincoln was a country lawyer in Illinois, somebody mentioned to him that his mind was not formed, and he was hurt. He said, "It's terrible. I mean, I'm a grown-up and my mind is not formed. I will form it." So what did he do? He went and he bought Euclid, unfortunately abridged edition, otherwise it would be a better country. Only first 7 books. And then the complete edition was not available at the time. And then he would spend every night while he was traveling from one small city in Illinois, to a small town in Illinois, to another, and sleeping in these communal beds. He was supposed to share a bed with fellow lawyers. Imagine, 4 lawyers in one bed. I'm talking about horror movies. So when the other lawyers would go to sleep, he would light a candle and he would read Euclid for years till he would be able to do every proof just like that. And he indeed became a great president. So do it, maybe you will become a great president. Well, or maybe it was a better time. Who knows? So, no, he did not, and they killed him eventually, as you know. So there is a pattern there. There is actually, going back to Pythagoras, there is a late legend that he was eventually killed by angry mob at Metapontum. So, it's a bad idea to study. So, what? And in the 7th book of Elements, actually, therefore, the book familiar to Lincoln, he describes what we now know as Euclid's algorithm. Right? He rewrote it. He and he made it into an algorithm from a procedure. The code which Pythagoras wrote was just a procedure. This is an algorithm. What's the difference? Why do I say that? You see, algorithm is a procedure which terminates. So, this is a terminating procedure. But of course, Euclid cheated. How did he cheat? When you read Euclid, what he says, it says, if we take 2 line segments, if they have a common measure, that's how you find the greatest common measure. Well, how do you know if they have a common? Right, so he guarantees termination by saying that they are integers already. Right? Let us look at the code. It is instructive. Notice that it's a fairly lengthy way of doing it. He starts with 2 integers, and then he does this subtraction. What would you do nowadays instead of subtraction if you're doing greatest common divisor? Mod. Percent. So didn't they have it on the keyboard? So why didn't they do mod? Why did they use a very slow version? Were they dim? They were not dim, they were great. But they couldn't do mod. There was a grave reason why they couldn't.
Did they have division?
They did have division. But division was awfully hard, very connected to what you just said.
Did have 0.
Why 0 is related? Why do you need 0?
Hard to divide Roman numerals.
Thank you.
Oh,
brilliant.
there you go.
Try doing it. Go home, write 2 Roman numerals, big ones, and try to do it. How would you do it? Like that, by doing subtraction. That's the best you could do. Long division requires positional notation. And positional notation was not known to the Greeks. It's not quite fair. Actually, a very great Greek mathematician, Archimedes, knew about it. He wrote a brilliant book, which was lost and rediscovered in the early 20th century, called The Cent Reckoner, where he introduced positional notation and 0, but as I said, it was lost. There is a reason for things being lost. There was a complete stop in mathematical progress in the year 211 BC. Why? Well, it's approximately, but in 211 actually, Archimedes got killed. This is why I picked 211.
Frederick Alexander? No, the Romans.
The Romans. Romans established dominance, established this Pax Romanum. You say, but Romans were very civilized. Yes, they were very civilized. And they knew perfectly well that all this theoretical stuff is just bullshit. They canceled all the grants to theoreticians. They said, we are engineers. We need to build roads, bridges, military machinery, missiles, whatever, small nuclear bombs, whatever the empires built. But all this number theory, they canceled. They didn't care. How do we know? You see, we have still extant Latin translations of Euclid. And they're quite amazing. They translated very carefully every single theorem from the first 7 books. They again dropped the later books, but they omitted something. They omitted the proofs. They were engineers. Engineers don't need the proofs. You know about it, right? You need to know theorems. I mean, it doesn't matter where they come from. All this axiomatic stuff. This is not necessary. So there was a new educational system which was built on memorizing things. And the progress stopped. It stopped for literally 1,500 years. Right? There's nothing in Europe. This is not quite, I'm lying because there's wonderful work by Diophantus, there's some other snippets here and there, but fundamentally the progress stops. Yes? We will get to Arabs, yes. It did not continue the way you would think. Sort of what happens, and Arabs were very great. They sort of, the great contribution, I will not have time to tell you everything I know about Arabs, but, you know, when we get to Arabs, and, you know, he was a Persian, but we count him as Arab, you know, same. What? Yes, he wrote these racy lyrics, which every Victorian person would read, hiding from his wife, but translated by Fitzgerald rather poorly. But in any case, he was also a great mathematician, and but he was just one of the bunch. They were very great. I mean, the center of civilization roughly at that time was in Baghdad. While all of us were climbing up trees and eating bananas or whatever, these guys were truly civilized and doing world-class mathematics, believe it or not. And later on, Baghdad was again bombed by Mongolian invaders and closed down, and then they sent a reconstruction team or whatever. But mathematics was gone from there. But Arabs preserved mathematics which they inherited from Greeks. Very early on, maybe 8th century, AD of course, they translated most of the Greek stuff into Arabic. And Europeans later on would rediscover Greek philosophy, believe it or not, from Arabs. For example, a lot of medieval translations of Aristotle were translated from Arabic, not from Greek. Greek texts were not available. They existed in Byzantium, of course, but sort of the sad reality is that what happens at that time is that Europe is, even Constantinople, where the civilization survived, was not making any intellectual progress. Arabs were doing marvelous stuff. Plus, they went to India and got the zero. So Arabs did these two fundamental things. They combined Greek geometry with zero and created what they called algebra. Algebra, right? This is an Arabic word. They created this new science, but it was not known in Europe till, well, I'll have to skip that, till roughly 1200. One of the great, and the sad reality, nobody ever heard this name. And there should be a statue on every town square. This is the guy who, again, transforms Europe, creates European mathematics, recreates it from nothing, and makes dramatic contribution. You might have heard his name, which was his nickname. He was also known as Fibonacci. Therefore, there is this ridiculous problem about rabbits. And, you know, we know about that. But he was the man who changed the world. How did he change it? Again, the similar story. A young kid, his father, he was born in Pisano, right? And his father was a trade representative of Pisa, which was a very major trade city at that time. Venice would very soon overtake it, but at that time Pisa was the main Mediterranean trading city, and his father was a trade representative of Pisan Republic in Tunisia, which was quite rich Arab place across the state. So he went with his father and learned Arabic and decided that he will go and travel throughout major Arab intellectual centers learning mathematics. But if he went to Cairo, which was a great, again, at that time, Baghdad was sacked, so he couldn't go to a great university in Baghdad, but Cairo was still active, so he went to Cairo, he learned Arab mathematics, he comes to Europe, and he publishes the first book on computer science. I'm not making it up. He publishes a book entitled Liber Abaci, Book of Abacus. What is abacus? Computer. Book of Computer. And what does he do in this book? He literally covers the first chapter, say, or the first. Those of you who know the second volume of Knuth, semi-numerical algorithm, when it deals with arithmetic operations, it starts with elementary methods. And Knuth describes the algorithm for long addition, long subtraction, long multiplication, long division, square root. Remember this stuff? You learned it in the 5th grade. This is the book. First time in history, somebody writes these algorithms quite precisely in a book of how to do these computations. And this is not a mean accomplishment. This is on what, this is the stuff on which the entire thing is based. Yes?
Was this a compilation, or was this...
It was quite original. He was a great mathematician. He was way above and beyond his teachers. Arab mathematics to that started to decline, and he actually was he was greater, in my opinion, far greater than even the greatest of Arabs who were dead by that time. So he was a wonderful, wonderful person, and he got recognized. Again, the amazing story about him is that the most powerful person in the world at that time, Emperor Friedrich II, Stupor Mundi, the wonder of the world, who was the most powerful person in the world, extremely well educated. He knew Latin, Greek, Italian, German, Hebrew, Arabic. You could say everybody knew that. No, nobody knew that. Nobody knows it. Nobody knew so many languages. He was extremely gifted person, wrote a canonical textbook on falconry. That's about how to hunt with birds, which at that time was considered a great science. Heard of Pisano. Right? Imagine President of the United States knowing the name of one living mathematician. That would be an accomplishment. So not... Well, nowadays it's worse. Nowadays, knowing the name of one dead mathematician would be an accomplishment. But he was so impressed by what he heard that he took his entire court, which was located in Palermo. Palermo is in Sicily. And they went to Pisa to have a mathematical competition. It's an amazing thing to do, right? Because it's long. There were no planes were not functioning or something. So the entire court goes there, and he had very good mathematicians in the court. Michael of Scott, Scottish mathematician, was his court mathematician, very good one. And they had a competition where Pisano won by doing some amazing stuff. He solved the 5th degree. He found root of 5th degree polynomial, which is not a mean task even nowadays. And he solved it with extreme precision, especially considering that he used based 60 fractions. At that time, that was the only way you could deal with fractions. That's what they got from Babylonians. We will see, it took a long while before people realized. Pisano discovered that you could use decimal notation. Arabs taught him for integers, but for fractions, he still did base 60. And, if you think about it, multiplication table base 60 is a tricky thing to memorize, right? So it was hard task. So he did amazing stuff, published many books, and rewrote our code. That's what he did. Modular. So it's much, much faster now, but it's still unsigned integers. There's no int. There is 0, but there are no negative numbers. Right? So from 1200, how long would it take for us to go and discover negative numbers and rewrite this algorithm? Could you guess? Almost 400 years. The next great man, and of whom for sure nobody heard even under Fibonacci, somebody at least heard of Fibonacci numbers. But in this case, this is one of the most amazing people ever born, and nobody knows who he is. So, and he came very close. I could say that he for sure knew what generic programming was. Because, the man was absolutely brilliant. He was a Dutchman. There was no Holland at that time. He still felt like a Dutchman. For example, he was one of the leaders of Dutch revolt against the Spanish. He actually became the most prominent military engineer in Europe of his time. And he invented this wonderful way to fight huge Spanish invading army by opening sluices and drowning them all. It's a wonderful idea. So, a small country was able to resist invasion from a superpower. Spain was like United States of today. So, Inquisition and all. So, he was a wonderful, wonderful military engineer, but then he was very great physicist. How great? Well, as great as they come. I mean, he invented the thing called force. Remember the thing called force? He invented the thing which is called statics. This is what is engraved on his grave. Feynman would always show it to his students and say, wouldn't you want this to be engraved, something like this be engraved on your tomb? Of course, you should say yes, because you would want something like that be engraved on your tomb. The idea is that this thing is not going to go around forever. There is a balance of forces. What Stevin discovered is what we know as the rule of parallelogram. That two forces, when you add them, you construct. Remember the rule of parallelogram? How you add forces? How you add vectors. He invented vectors. So, oh, it's trivial. It's how you add. Nobody knew about vectors. He invented vectors. He invented this abstraction called force, right? He also did some remarkable thing in hydrodynamics. I mean, another major contribution in physics for which he gets no credit at all is 3 years before Galileo, he did the experiments and published the results that if you drop bodies of different weight, they will accelerate identically, right? You always hear that Galileo discovered that. No, Stevin discovered and published it, but he was not an Italian superstar. He was this humble Dutchman. I mean, the country did not even exist, so people did not pay any attention. In my opinion, a far greater man than Galileo, right? Now, but Galileo got this, publicity stuff with the church. So that's what, truly, I mean, and Stevin, nobody knows about him. You say, so what it has to do with mathematics? It has everything to do with mathematics. For example, he's the guy who invented negative numbers. This is not bad. Negative numbers is a big thing, yes? So you should be immortalized for that. Well, after that, he invents decimal fractions. Should be immortalized for that. After that, he invents infinite decimal fractions, real numbers, and describes all the operations on them. For that, right? So he rewrites it like that. He knew Euclid's algorithm. He knew this code very well. And then he does something which, from my point of view, is really astonishing. Okay? So he did all this physics. He did all this number stuff. Then he looks at something which does not exist. There is no name for it. And he comes up with this code. So he invented templates, something like that. That is, he discovered what polynomials are. Right? That is, didn't people know about polynomials? No, they knew that you could describe polynomial as an algorithm. You could write code, take x, raise it to the third power, take x, raise it to the second power, and multiply by 5, and so on. I mean, describe the action. But they viewed it as a piece of code, right? Or function, piece of code, yeah? What Stevin realized that you could view it as a piece of data, and you could have operations on it. You could write polynomial as data. Going from functions to data is such a dramatic step, right? And then he describes carefully that you could add two polynomials. Now, since they're data, you could operate on them. Before, only polynomial operates on a number, right? Now, you could operate on two polynomials. You could add them, you could subtract them, you could multiply them, and you could even divide them and get a remainder. Therefore, you could do greatest common divisor of polynomials, right? That is, you could find if two polynomials, simply speaking, have common roots, which is a very hard problem in general if you think about it, because we cannot find out if one polynomial has roots or not. It's a hard problem. Here you take two and could find out whether they have common roots, and there is a trivial thing, it is just Euclid algorithm. So this step of being able to generalize from numbers to see the same rules applying not to numbers but to programs was a tremendous step. You know, I have no words. When I think, I mean, you have to put yourself back in history. Of course, for us, it seems self-evident. Of course, you could view polynomials as a sequence of coefficients. That's because we were taught that. He discovered it. He sort of figured out that you could do that, and then you could do operations, and you could add programs together. I don't know whether I make myself clear, but tremendous step. I have to skip many great people and get to another sort of wonderful person. And now, for quite a while, we're going to look mostly at Germans. A great German mathematical tradition is born. We sort of forget it now, but in 19th century, Germany was intellectually the dominant country on earth. I mean, everybody else were barbarians in comparison. Gauss eventually becomes a professor in Göttingen, a very small German town. He was, if we look at his successors for the next 100 years, it goes like that. Gauss, Dirichlet, Dedekind, Riemann, Klein, Hilbert. I don't know whether any of you understand. This is like half of great mathematicians in history in this little town in a period of time of 80 years, right? So great, great tradition. And Gauss, in some sense, is a creator of modern mathematics. And what I mean by that is that Greeks created this axiomatic method of writing mathematics in this formal way. Euclid was the textbook. Then came this new mathematics, Leibniz, Newton, but that was like recipe books. There was no, it was not viewed as mathematics. It was not axiomatically based. The only person who was able to bring the first person who was able to bring the Greek rigor to non-Greek mathematics was Gauss. In the year 1801, he published a great book called Disquisitiones Arithmeticae, which means investigations in arithmetic, which is basically the first modern book on number theory. Do you know modular arithmetic? Yeah, he invented that. Well, other people, Lagrange of course knew that, but he didn't know that it was modular arithmetic. Sort of Gauss was able to write it down as sort of as we write it, notation, everything. It reads, the book is translated into English and reads wonderfully. And he set a formal foundation for many number theoretic results, including the fact that he was able to prove the fundamental, one of the most fundamental results called the fundamental theorem of arithmetic. Gauss is actually great. He proved also the fundamental theorem of algebra. You cover all bases in one guy. Fundamental theorem of algebra, this is that every polynomial has a complex root. This is very non-trivial result. He was the first person to give solid, rigorous proof of that. Fundamental theorem of arithmetic is that every number is decomposable into a sequence of prime in a unique way. Right? Greeks knew that, but didn't quite know how to prove it. They did, but it's a complicated story. But Gauss was able to write it rigorously, beautifully. He was very, very proud of this result. Therefore, he said, let's abandon Euclid algorithm. So let's see what we can do guys. I hope we'll have questions after that. So he came up with this thing which says that you could factorize every number into a sequence of prime in a unique way. Then he comes up with the following wonderful, I put quotes, you see quote, wonderful algorithm for finding greatest common divisor. He says, let's take two numbers, let's decompose into the sequence of prime, let's pick common prime factors, that gives greatest common divisor. Since he was such a great mathematician, every elementary textbook of arithmetic in every European or American school since then describes that. as the way of finding greatest common divisor. If you go back to your childhood and remember, that's what they told you. Nobody in his right mind prior to Gauss would tell you that. Why am I saying it? Why is such a stupid idea?
It's hard to find.
Yeah, because you don't know what they are. I mean, it's, it's...
And this is like the object-oriented design approach where they say first identify the objects.
Exactly. Exactly. Yes. Well, don't start me on objects. But it is amazing. One of the greatest mathematicians of all times gets so confused that he replaces a beautiful, extremely fast algorithm, Euclid's algorithm, which is basically logarithmic in size, with a thing which basically non-terminating. He was actually smart. I should have quoted the whole paragraph, because after that, he continues. There is a parenthetic remark. And for those cases when it's hard, there is an elementary method for doing so. This is amazing thing. That is, he basically describes an algorithm and then sort of puts a parenthetic remark. This is awful algorithm, don't use it. There is somebody else old one. Yeah? So, but he wouldn't mention Euclid algorithm in the entire book. Brilliant book, except this amazing omission. The most central algorithm from which number theory starts is omitted. Because he was so proud of his discovery. But again, he was too great. Man was marvelous. Do not misunderstand what he did. Do you know that he invented telegraph? He would do all kinds of things. He would jump on every opportunity to do new thing. Inventing telegraphs. Then they started doing geodesic survey. So he said, oh, I'll go help. And he invented differential geometry. Hello? Well, he did invent differential geometry, no matter what it says. So, right? And he would do this thing. He would look for any opportunity to do something brilliant. Most likely he invented, we know that he invented non-Euclidean geometry, but didn't publish. He let Lobachevsky publish it. He learned Russian to read Lobachevsky in original. Well, piece of trivia. Gauss and Lobachevsky had the same high school teacher of mathematics. Isn't that amazing? How could it be? I mean, one guy grows up in the middle of Germany, another guy in the middle of Russia. Because Gauss was much older. His teacher, who taught him when the teacher was quite young, decided that the pay was bad and he moved to Russia. So whether there is something in that or not, I don't know. But the same guy taught both, which is quite remarkable. But Lobachevsky is the guy who sort of officially invented non-Euclidean geometry. So Gauss, he publishes this stuff in 1801, and time passes, and he notices that he could do some interesting thing with complex numbers. He was the first person really figuring out what complex analysis was all about in a rigorous way. Then he noticed that some complex numbers are special, that the numbers a plus bi, where a and b are integers, give you a very interesting set of numbers. Okay? So special that nowadays we call them Gaussian integers. So if you invent something like that, they'll name it after you. And what he discovers is that Gaussian integers possess many of the same properties as ordinary integers. There is unique factorization into primes, right? Which is a remarkable fact, except the fact that 2 is not a prime in Gaussian integers. If you take Gaussian integer 1 plus I and multiply it by Gaussian integer 1 minus I, you get 2. So 2 is not a prime. But then what he discovers, that you could do GCD on Gaussian integers. That is, you could, and GCD is fundamental for a whole bunch of things. That what Gauss starts realizing around this point, this is 1829 roughly, I think it is 1829, he starts realizing that there is this connection between ability to use Euclid algorithm for something, and unique factorization. And he doesn't quite know it in these terms, but he gets a hint. And that is a fundamental hint. It's such a fundamental hint that his successor as a professor of mathematics in Göttingen, this guy, Peter Dirichlet, sounds French, but in reality, perfectly 100% German guy, realizes the following amazing thing. This, I'm not even going to tell you, ask you to read the quote. He realizes that Euclid algorithm is the foundation of number theory, and therefore it's foundation of mathematics. That is, he realizes that in some sense, any effective proof of unique factorization on which everything we do with numbers depends on Euclid's algorithm. I mean, brilliant insight. In any case, he starts lecturing on number theory. He writes the second most important book in number theory history. Gauss's was the first one. Dirichlet writes the second one, which is his lectures in number theory, except he doesn't write it. You see, he was very lucky. While he's lecturing, he has a very good guy sitting on his lectures, whose name is Richard, or Americans say Richard Dedekind, this guy. Was an amazing person, again, absolutely humble guy who would, being a fellow professor of Dirichlet, would sit in Dirichlet's lectures and take notes. Then he would take these notes, write them as a book, add 80% of the material, and publish it under Dirichlet's name without even mentioning his own contribution. And he realized the following amazing thing. He looked at what Gauss did with Gaussian integers, and he said, but there are many other integers like that, integer-like things. He could say, we could take numbers of the kind a plus b times, say, square root of minus 3, and many, many other kinds of integers formed out of, if you like, solutions of polynomials with integral coefficients, and he calls them algebraic integers. He creates a theory of algebraic integers. And why is it significant? Because you see what he realizes. He takes the notion of number, and before that we had integers. People realized there were rational numbers, real numbers, complex numbers, maybe Gaussian numbers, 5 kinds of numbers. But that was it. Maybe somebody in Ireland discovered some funny numbers called quaternions. Hamilton did, but 6 kinds of numbers. What Dedekind does, he discovers infinite families of numbers, all different, all with different algebra, right? And then he discovers amazing result, which is very profound, that he didn't quite know. I'm going to use I'm going to tell you a little bit more than what he discovered because it's easier. That Euclid algorithm doesn't always work for these numbers. For example, for numbers of the kind a plus b times square root of minus n, it works for n equal 1 Gaussian integers. It works for 2. It works for 3. It doesn't really work for 5. And after, say, 15, it stops working completely. Sort of really gets into big, big problem. And this has tremendous consequences because then this is sort of showing some light to something completely different, is that if it were not so, if Euclid algorithm worked for all algebraic integers, there would exist marvelous, very simple proof of last Fermat theorem. But that's, life is not fair. So, but Dedekind discovered this infinite family of things possessing similar algebraic structure, right? What we now would call ring. He said that, what is iterator? It's infinite family of implementation. Sorry to bring STL into that. And this is the same. I mean, he discovers that there is set of requirements for which there are infinitely many implementations, all very interesting and different, right? What he does not do, and he is very great as a mathematician, he also comes with sort of many brilliant results and foundation of analysis. Dedekind cuts, some of you might have heard. He helped Cantor greatly developing set theory. Tremendous guy, and very humble. I mean, he would never sort of claim credit for anything. I wish there were more scientists like that, but the fact is that what he was not able to do, and we will have to wait another 20 years, say, 30 years from his time, he was not able to say that we could drop the implementations. We could just keep the requirements. There is this, and you say, oh, this is very simple. No, it's not simple at all. The fact that you could operate with requirements without looking at implementations, that you could view numbers as a concept, not as a thing, is a tremendous step. So who did this step? Who actually discovered this thing? Okay, this is somebody which, again, so many people do not know, and the person of great genius. In some sense, she invented abstract mathematics. And I'll give you very solid quotes for very great mathematicians saying that. It's not my opinion. And again, the person who never gets credit, nobody knows about her. Even when she lived, nobody knew about her. Right?
Physicists know about her for a completely different reason.
What?
Physicists know about her.
Yes, she proved, and Einstein thought it was one of the most remarkable things, that conservation laws and symmetry invariance are identical. This is so-called Noether theorem in invariant theory, which physicists know, which would be a great contribution by itself. But she did far, far greater things. And under such duress, I could not even tell you. She gets her doctorate and couldn't get a job any place in Germany. The year is 1903, no woman could get an appointment in any university in Germany. People start realizing that she's wonderful. And what do you mean by people? David Hilbert, the greatest mathematician of the age, realizes that she's somebody totally outstanding. He couldn't get her a job. He's a professor at Göttingen, the same place as Gauss. No way. So what does he do? He invites her to come and teach under his name. That is, she couldn't get a job, she couldn't get paid. So Hilbert would announce a course on such and such thing, and then put in parentheses, taught by Emmy Noether. That is, it's his course, he's the professor, he's getting paid, but she's teaching. This lasted for, I guess, 12 years. Eventually she gets some kind of visiting appointment, but with no official status, quite sort of unfortunate situation. She becomes world famous. Students come from all over the world. And she's probably the most generous mathematician of all history, maybe the most generous scientist of all history. He never publishes anything under her name. She gives her results to her students. It's supposed to be the other way around, right? You put your name on your students' papers. No, she would give them her results and not put her name on the papers. This is an amazing person of greatest possible generosity. And she discovers, what does she discover? Well, let me finish her life and then I'll tell you what she discovered. Very unfortunate. So on top of that, she couldn't get a job, plus she's Jewish. And why is it a problem? Look when she lived, right? So in 1933, she has to go, right? Because they wouldn't let her even lecture or do anything. I mean, they were not killing them yet in 33. So she comes to the United States. She's at that time, when she arrives 34, she's the greatest mathematician on American soil, arguably the greatest mathematician of her generation. Does she get a job? No, she's a woman. Eventually, she gets a visiting appointment at Bryn Mawr girls' school. They could trust her there. And she was quite happy. I mean, she had a roof, and she made friends. Unfortunately, she dies. She didn't last long. Again, what did she do? And here let me quote, again, somebody, since no matter what I say, it's not going to sound as well as read the first quote. Pavel Sergeyevich Alexandrov is a great Russian mathematician who invented point set topology. So by itself, a very great person. This is from his obituary. When Noether dies, he writes, "It was she who taught us to think in terms of simple and general algebraic concepts, mappings, groups, rings with their ideals. She invented modern abstract mathematics." She taught all of these guys. And, you know, not all of them would acknowledge that. Because, again, being taught by a woman, I mean, what a shame. But some did, quite publicly. Did she write anything in abstract algebra? She wrote a little tiny bit. But most of the stuff was not written by her. It was written by one of her students, Bartel van der Waarden. This is the next guy. There's this picture. As a young kid, he gets his PhD in Amsterdam, I believe, and he goes to Göttingen to learn from Noether. He takes notes of her lectures and then publishes them as a book called Algebra, or called at that time Modern Algebra. Now it's called just Algebra. This is the first book which talks about groups, rings, fields, vector spaces, modules. The 2 volumes, it's still in print, it's still wonderful, wonderful book. And he says, actually, right on the thing, he says it's based on her lectures. But she didn't even bother to publish what I would claim the greatest thing which happened in 20th century mathematics, the abstract math. What is the idea? You could separate concepts from implementations. You could just deal with concepts. You could talk about group as a concept without this group or that group, or ring, right? So if anybody invented generic programming, she did, of course, right? Stevin discovered sort of marvelous things, but he didn't fully was able to do that. Dedekind did marvelous things. She realized it all, right? She realized that you could fully separate these 2 things. And again, the thing is not finished. The beautiful thing about science that it's never finished. We'll talk about it. But again, her contribution needs to be remembered, and you know, I wish again people would know about her. So are we done? Do we know now? And this is the way she writes this algorithm. Okay? Well, okay, maybe not in C++, but it's literally what van der Waarden wrote. That is, she says that this algorithm works on Euclidean ring element. What is Euclidean ring element? Well, this is the whole trick. It's the set of all the things on which this algorithm works. This is, but you cannot imagine how brilliant it is. Yes, it sounds somewhat tautological. I mean, you do not do that. But the fact that you just say that we need to write all of the requirements, and if requirements are satisfied, this algorithm will work. And this would. Yes.
So that's a provable fact, whether on a given element it will work without actually going through all the stuff.
That's the definition. She does not need to prove anything at this point. She just says, I'll call this domain of things Euclidean ring, or Euclidean domain is another term frequently used, if this algorithm works. I mean, you don't need to do anything. Then you need to prove that this particular thing is a Euclidean domain. You see, I didn't need to prove that iterators work. Iterators do work by definition. It's to prove that some particular implementation is an iterator. You need to do something. Say iterator works, it's self-evident because it's by definition iterator. It is just a definition. Iterator is not a class. It's a set of, it's exactly the same idea, right? Except, what I realized was that it's not just algebraic things. It's data structures where you could use the same method as Noether used for algebra, right? And mathematicians use throughout, it's done throughout the entire mathematics. Mathematicians learned this amazing trick. It's a shell game. What they do nowadays, they say, oh, we don't need to look at the details. We'll just look at the, definitions. They write all these definitions. Oh, it's wonderful. And this is a great, great danger, because sort of what Noether knew, she knew millions of implementations. Younger generation of mathematicians forget them. It's not that Noether didn't know particular Euclidean domains. She knew all of them by heart. And then she abstracted. What happens, modern math happens, as like people learn the definitions, but they don't know the basis. This is a great danger, because abstraction is wonderful when you abstract from something. You cannot start with abstraction.
It's the Roman approach to mathematics.
Yes, but in a different sense. It's the ignore the reality, concentrate on definitions.
You run into the danger of proving theorems about definitions that have no implementations.
Absolutely. Yes, 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 yes. And it does happen. I mean, you know, people publish papers, and you wonder, I mean, do these things exist? No, they exist by definition. I mean, you write definition and say, but does it exist? Sort of, but there is the sad reality, the question, sort of, it's a complicated thing. I don't want to go into that, but it exists in computer science, especially in theoretical computer science. Which, you know, you see these young students writing these theory papers which are not based on anything, right? So Noether was not like that. I mean, she was a really great mathematician. All her definitions were based on working algorithms. This is a working algorithm. She lifted it and she says that now let us just use it whatever we can. So now we could sort of look and see, does it fit here? Does it fit there? Right? And sadly enough, even now we do not quite know everything about it. So let us look at a couple of the problems. One problem, who is the greatest computer scientist? Donald Knuth, no question. I'm not joking. So I show this piece of code, the previous thing, at Stanford. Knuth is there. Oh, Matt was there too. And he says it's wrong. It's very unpleasant. Oh, you show your code and Knuth says that it's wrong. Man. No, it's a humbling experience. That's what I show. And that's how he proves that I'm wrong. He says, look, let's take this code, let's plug 1 and minus 1. And what do you get? You get minus 1. Minus 1 is less than 1. Therefore, it's not the greatest common divisor. Is he right or what? Well, I had to argue. You have to stand your ground, Knuth or no Knuth, right? So I'll teach you. If you learn anything, this is a universal answer. Always works. And so, your boss tells you the wrong code. Depends on the definition. Clinton used it too, but I didn't. So I have nothing against Clinton. I mean, you know. But he used it. My disciple. So, but this is the correct definition. Why do I say that I'm right? Let's go back and look at Knuth's code. Why do I argue with him? He wants me to put this line here. It's a very simple fix. Yeah. Yes? And I say he's wrong. I could be stubborn, I could be mad. After all, he's Knuth. Yes? He knows about algorithms. He knows about Euclid algorithm. I say this line is wrong. Why?
How do you know that you can compare a Euclidean ring element with 0?
Well, it's a ring. Ring always has a 0. It's a correct question, but you didn't ask it correctly. It's a hint.
My question was, like, if you look at the Gaussian integers, how do I know?
Gaussian integers have a 0. Gaussian integers have a 0.
Is I less than or greater than 0?
That's where the problem is. It's not the 0. It's the less than. What he asked me to have, he asked me to assume that my ring is totally ordered. I will not assume that because there is no total ordering in any meaningful way of Gaussian integers. They're on a plane, they're not on a line. The same thing for polynomials. There is no. Moreover, the problem is that it's very hard with Gaussian integers to figure out sort of whether, say, which one, I or 1 is greater. I mean, in some sense, they're equal. Remember, I, the square root of -1, and 1. Do you understand why I say that they're sort of equal? The distance from 0 is actually the same. And I would claim that 1 and -1 are sort of equal, even for regular integers. Sort of. Especially in terms of divisibility relations. And I will say things like they might go past, but maybe not. Mathematicians, when they talk at a ring, they define things which are known as a multiplicative group of units. These are things which sort of are like 1. Like in Gaussian integers are things like 1, I, minus I, and -1. They all sort of, they're units. And the idea is that multiplication by unit is free. You know, when you look at the prime decomposition, you could multiply by 1 as many times as you like. In a sense, you could multiply by -1 several times. Think about prime decomposition.
They're sort of closely related to the multiplicative identity, and so using them somehow doesn't count.
Does not count. Especially, again, let's look at the regular integers. You know, 6 is 2 times 3, but it's also -1 times -1 times 2 times 3. We have to factor this -1 stuff out. It does not matter. That is, in terms of divisibility relation, and that's what we need to use, right? So we need to change our definition of greatest common divisor. That greatest does not mean this. It means some other greatness. And what is the greatness of which we talk? What is the definition which we are looking? This is the definition. The greatest common divisor is the divisor which is divisible by any other divisor. I'm not comparing with less than. I'm comparing using divisibility relationship, which is given to me. Right? So think, yes?
First of all, I'm not sure that I agree that the example of 6 equals 2 times 3 times -1 is a good example, because you posited the fundamental theorem in algebra, which gives you a unique decomposition, so you can't...
Arithmetic.
Sorry, arithmetic. So you can't go back and...
For positive integers.
Yeah, but you started with 6. I mean...
But 6 as a whole number, I could decompose in 2 different ways.
Well, you can decompose it in more than 2 different ways. You can say that it's 2 times 3 times 1 times 1.
Yes,
So,
exactly.
right.
Exactly my point. You have to take units out. Units do not count.
Sure. But you started by saying that mentioning that there is a unique prime factorization a long time ago, so I'm not sure that, I'm just not sure that I like you taking that out and now saying that, well, look, there are multiple ones.
But unique prime decomposition depends on the notion of a unit. Otherwise, it stops working. That is, you have to consider 2 numbers being equal in terms of divisibility if they are equal modular units. 6 is equal -6. In other ways, you see, I give you another example. You could put arbitrary number of, you need to decide, I mean, do you have unique prime decomposition for integers, including negative numbers? You want to have it, but you don't unless you accept my definition, because otherwise you also get -2 times -3 are equal to 6.
My second question is, given this definition, how do you deal if -1 is divisible by 1 and 1 is divisible by -1, but you are now eliminating 1 as a possible factor and only leaving -1, right?
No, I'm saying they are in a sense that I'm throwing away uniqueness. You have multiple greatest common divisors. This is the trick. You have to get rid of it because you do not know which one to pick. Because you get, again, let's go into Gaussian, or let's go into polynomials. For polynomials, what is your multiplicative group of units? This is the entire, for polynomials over R, real numbers. Multiplying by a real number is a unit. 2x plus 1 and x plus 1/2 is the same polynomial.
Yeah, so this whole problem now decomposes into equivalence classes, which are distinguished only by whether they have ones and minus.
Exactly, yes. Or units of whatever kind. For polynomials, these are not ones and minus ones. They're every, multiplying by any coefficient is free. Yes?
Yeah, so the algorithm returned one of the two valid answers.
One of many potentially valid answers.
Well, in that particular case.
In the particular case of 1 and minus 1, yes.
Yeah.
But if you give polynomial general potentially infinitely many equivalent answers, right? I mean, it's not satisfying that you have this, but this is otherwise mathematics crumbles. You have to do it, right? So I had to fight Knuth. It wasn't just my mean-spiritedness. That helped. That helped. So, right? So we still do not know what Euclidean domain is from my point of view. Why don't we know it? Because you see, over these 2,500 years, we learned a lot. We clearly learned a lot, right? I showed you a tiny little fraction of what we learned. It's a lot. But we still, even with this simple algorithm, we do not quite know everything. We do not quite, that is, when Noether said that it has to be a ring, she lied. It doesn't have to be a ring. You see, it works for a semi-ring. I mean, it's a perfectly good algorithm to use on positive integers, which is not a ring. Minus is not defined. Yes?
By definition, isn't a semi-ring a ring then? Since you said that anything that works on it is a ring.
No. It's not how she defined it. She defined it on a ring. She over-specified. She said that Euclidean domain is a ring with additional properties.
But earlier you said the whole definition of the ring was anything that worked on the definition.
No, I lied. Well, it's a ring on which this algorithm works. I mean, it is Euclidean ring. What is Euclidean means this algorithm works. What is ring? It means that you have lots of other operations. You have plus, times is distributed over plus is commutative associative, times.
Misunderstood
Right.
Qualified.
Right. So, well, I cut lots of corners in this presentation, guys. I mean, quite intentionally, because, I wish I could teach everything like that in depth, but you would have to give me a little bit more time. So, fair answer, yes. Now I could do a fairly good job with 2 semesters. So what I'm saying is that mathematicians still overspecify it. Now, any mathematician, especially modern mathematician, who learned from these abstract books, if you ask them, could you do this algorithm on rational numbers? What do they say? They say no, right? They say no, absolutely not, for real numbers, because you don't have any remainder, you just do division completely. Something is wrong, because Greeks could. It's a perfectly wonderful thing to find greatest common measure of 2 rational numbers. Is the smallest rational, right? Why doesn't it work anymore? We overspecified. We did not realize that we have to be very careful how we define our remainder. We could define it so that it works for rational and real numbers. And actually, sort of good mathematicians understand that it does. But in textbook mathematics and the stuff which is taught, it's sort of gone. It does not apply. While it's a perfectly valid and wonderful thing to do. Because, let me do number 3 and then come back to number 1. So we do not know what are intended models. There are models which we lost along the way. Then another thing is that the world is marvelous in the following sense, that the same set of axioms has this whole bunch of good things affiliated with it. Like iterator is such a simple set of axioms, such a simple set of requirements, that all these algorithms which come along, right? You get them. What we missed is that there are a whole bunch of other algorithms on the same set of requirements, and they're not described. Some of them are. But, you know, what else could you do? Well, there is a marvelous algorithm, which again, I don't think I could cover, which is called extended Euclid, right? Which, again, somebody, Scott, could you post this thing on your website? Oh, yeah. Because then they could read the code carefully and figure out what it does. There are other algorithms. This stuff is intimately related to extremely important and powerful computational abstraction, also very old, Greeks knew about it, called continued fractions. This stuff which now nobody knows anymore. This is a wonderful sort of thing in elementary mathematics which sort of not taught anymore. And very powerful results. And sort of continued fractions that could give me 1 minute. It is interesting enough, so let me go back. What you could observe is that we could continue this process. And when we continue this process, we observe that we get a sort of sequence which goes like that, infinitely, which is, we have a remarkable fact. Irrational quantities, square root of 2 is an irrational quantity, has a finite representation as a continued fraction, right? Because we know, like we do not know all the decimal digits of square root of 2. I mean, this is some just of random stuff. I mean, they're truly randomly distributed, or so we believe. We don't have a proof. But we have a wonderful, concise representation of square root of 2 using continued fractions. And Greeks realized, and Lagrange in the 18th century formally proved the following remarkable result, that any quadratic irrationality, that is a number of the sort of like a plus b8 be irrational times square root of n some integer, could be represented as a periodic continued fractions with some period. And the other way around. Every periodic continued fraction represents quadratic irrationality. They called them surds in the 18th century. They didn't know anything. They had these funny words. So, but, right? So, which is this remarkable result. And what we know now, sort of when we look back, that Plato was challenging mathematicians of his time to find similar clean representation of cubic irrationalities, and we still do not have it. I mean, it's still an open problem. But sort of all these continued fractions are marvelous stuff because we know that continued fraction representation of any real number gives you the best set of rational approximations to it in some sense. It's wonderful stuff in terms of even real numbers. So what I'm saying, this algorithm, and Euclid algorithm actually generates, if you like, the continued fraction, sort of the set of remainders. And we do not have it. Again, the stuff, if we want to build STL for number theory, we need to write these requirements and a whole bunch of algorithms which will do all of this stuff. The work is not done. So just showing how, 2,500 years and we haven't started. Now, this is the amazing stuff. So 2,500 years, we have this algorithm. Every great mathematician, or just about, worked on it. We know it by heart. In 1961, somebody of whom I know almost nothing, and I have no picture, I wish I could, by the name of Joseph Stein. He's an Israeli. That's the only thing we know. He worked in Raqqa Institute, which is part of Technion. Technion is a university. That's the second thing we know about him. This is it. Why do we know? Because he published a paper where he gives his affiliation, where he describes a better algorithm for greatest common divisor. And that is an amazing fact that, you know, for such a beaten problem, basically recently, yesterday, 61, you know, I remember 61. I mean, it shows. So, he comes up with brand new algorithm. Again, I don't think I could run through the code, but I'll give you the idea. The idea is brilliant. You take two integers, and you say, if they're both even, then we could factor out 2. This is a shift, and move this 2 into greatest common divisor, right? If one is even, another odd, we could just divide even by 2. This 2 is not going anyplace, right? And if they're both odd, we could do a subtraction. That will make one of them even. We could keep shift, right? Till they become equal, then we will take this. So we do roughly 1 bit of one integer per iteration. We either shift one or the other, or we do subtraction, but you know, sort of it's logarithmic and practically speaking very fast, because the modular operation in C is a slow thing. Takes 17 cycles on Intel. Shift is also slow on Intel. Intel is lousy processor, but it's like 4 cycles nowadays, right? Much faster, right? And on most RISC machine, shift is single cycle, right? The good processor designers know how to do shifts. And I think actually I suspect that only Pentium 3 is a very slow shift. I think Pentium 4 is 2 cycle. Anybody remembers? I mean, it's faster. It was 4 cycles on 3. I forget. So this is a wonderful algorithm, right? So why I'm telling you about it? Because it's a different algorithm for the same problem. It works for integers. Does it work for other? Yes.
I was about to ask you exactly that question. I don't think it's an algorithm for
knowing me, you know that I'm going to go into that. So does it work for other domains? It works for integers. The amazing thing, which is not commonly known, is that it works for polynomials. What is an odd-even polynomial? Well, think about it. What is odd and even polynomial? What is a shift operation? You could shift polynomial if you could divide it by x. So if the last bit is 0, the free coefficient is 0, that's your shift. And how could you subtract to make it 0? Well, remember that multiplication by a constant is free. It does not matter with polynomials. So you could always make for 2 polynomials, their last free coefficient be equal, then subtract, right? It works. This is totally amazing. When I realized it, I was running around screaming. Seriously, I'm not joking. Because you say, how could, and then a year ago, there was a brilliant paper in Germany which showed that you could use this algorithm for Gaussian integers.
There's a shift there.
I knew, but I forget. I went through the paper, but I forget. It's fairly complicated. The references at the end, if you look, the paper which does that is this, Weilert. Right? Yes?
So if I can put that a different way, the algorithm still works, but the value of 2 changes.
Yes. Dramatically, yes. Yes. And the value of 2 is rather large. It's x, it's anything, right? And the value of odd even change, I mean, yeah, it's, yeah, yes. But
And shift changes too.
shift is sort of the same if you think about it. The bit changes. In integers, 1 0 lives in a bit, yes? In a polynomial, coefficient lives in a bit. So the bits are these big things which contains real numbers.
Excuse me, so the 2 changes, bit changes,
Yeah.
and even and odd changes.
Well, no, the 2 is.
What are the matters the same?
2 is the width of the bit.
But the algorithm is the same. Yeah. Yeah. This. Yes. Thank you, Scott. That is the whole point. What is the difficult thing? So what is it? You see, while we do not have really perfect definition of Euclidean domain, we sort of have some definition. Noether came up with a definition, and I think that we could sort of fix it. In case of Stein domain, Stein, of course, never knew that he was inventing a domain. He was just publishing a minor, the paper, just look at the name. Computational problems associated with the Raqqa algebra. Raqqa is the name of the place he worked for. Nobody knows what Raqqa algebra is, so don't anymore. The problem he was solving is not interesting. It's the algorithm he came up with is very interesting, yes.
Is he still alive?
I know nothing. I buy lunch to anybody who gets me his picture.
With this internet connection, Scott, it's gonna take
I looked, I did Google searches backward and forward. I do know that he's from Israel. I did find this stuff. So I found some references. But I could not tell you, I could tell you. A year ago, he was still listed as an emeritus there. So I would think he was still alive. But I cannot get his picture, nor do I know anything about him. And I like knowing things, as you have probably figured out by now. It's disconcerting that nobody knows anything about him. People don't even know about him at all. He's not a household name, trust me.
I bet you're asking the wrong people. I bet he's a physicist.
He is a physicist, yes. But physicist, he published like 1 paper. Matt, please find out.
I probably know people who know people.
You might have met him in your youth. No. He might have was visiting your father. Maybe. So, in any case, I wish I knew more. I do not. And I spent time looking.
Does he know you solved it for polynomials?
No. I don't think he views himself as a computer scientist or even interested in this stuff. He just published a paper, 61. Think about it. It's a long time ago.
What we need to do is we need to solve for the greatest common acquaintance.
Right. So the question which is still pending is, what is Stein's domain? What is the set of requirements which will make his algorithm work? Right? I don't know the answer. This is for the younger generation, for you. It's actually, in some sense, the whole point of, when I give this talk, and I have given this talk, you wouldn't believe how many times. Because, I gave this talk, and I decided that from now on, I'll never talk about STL, because this is much more interesting talk than anything I could say about STL or stuff. Plus I could show pictures. So my whole point is sort of that you guys will do it. In some sense, other people should, I am sort of, my next step is, the cemetery. So, the younger generation should pick up and should use this. Not necessarily, I'm not saying do Stein domain. This is an example, okay? What is the point of the talk? Is that these abstractions, first of all, that mathematics matters. I really want to send a very strong message to every single person I ever meet, that mathematics is important, that it does form our minds. Yes, Plato was right. Yes, Lincoln was right. We live in the culture which despises mathematics. People pride themselves. You meet perfectly wonderful people who tell you, oh, I hate mathematics. I have friends who are Stanford professors, humanities, who say, I always hated mathematics. They would never say, I always hated music. This is not cool. But saying, I always hated mathematics. It's a cool thing to say. It makes them like, they are not nerds. As if, I'm sure you met people, who say it proudly, right? And computer science, we're just We're just heirs of this great tradition. We're not doing anything new. Now, every time you program, you step into this tradition. However humble your program is, you're still doing things within the same tradition. Programming was invented by mathematicians. Von Neumann, Turing, guys who came in the same line. So it is mathematics. Right? It's not necessarily mathematics in terms of obscure differential equations. Mathematics is not just obscure differential equations. It's the worldview. It's the view where you search for these beautiful abstract things. You search for elegance. And when we program, we have to search for elegance. It's not that it pays, it doesn't, trust me. I mean, there's absolutely no pay, and no venture capitalist. If you go and say, I want to do beautiful stuff, you'll get funding. Yeah.
He's at Hebrew University of Jerusalem.
Wonderful, thank you.
You're welcome.
Get a picture?
No, but a paper that he worked on.
Recently? Recently?
Is it a different paper?
Apparently he was a visitor at University of Texas for a while.
You're a better Google person than I am. That's for sure.
1997, as a matter of fact. Wow.
Wow.
How do you know it's the same Joseph Stein?
It's likely. If it's, it's very likely.
Israeli physics professor named Joseph Stein?
In Israel, there could be two. This is not a very, it's not a very rare name if you think about Jewish name Stein. Stein is very common, but it's very likely it's the same person, yes. So keep looking for the picture. Yeah. So, right, so the point of this, again, going back to my conclusion, what is the point? The point is that, we do this stuff, and we should strive to do it as well as we can. We should look for abstractions, we should use formal methods, even when we write XML stuff. This is, No, but I used formal methods doing C++. Who would have thought that you could use axioms dealing with C++? Okay, I did write axioms and still do. You could ask Sean, he sits next door to me, and he comes to my office and helps me with axioms, right, for what I do. I mean, I do that. It does help tremendously. You cannot understand. So this is the message of the talk, if anything, right? Again, I'm not trying to peddle. This is not a, extreme programming talk, I make no money on my talks. I do not sell books. So, but I do believe it's true. So this is the message. Questions or? Okay. Sure. This or before? This is the code. This is sort of explanation. Yeah, these are identities on which it's based.
Implicit template. But when you apply this to polynomials, 2 becomes x, right?
2 becomes x, yes.
Show the code.
So does 2 still become x when you do polynomials with integer coefficients, or do we know?
Pardon me? No, it doesn't work for polynomials with integer coefficients. Nothing works. Euclid doesn't work for polynomials with integer coefficients. It's only over a field. You have to have reals. Otherwise, you couldn't have division. There's no even remainder division. Think about it. How do you divide 3x plus 2 over 2x plus 1? You don't. Right. That is, you need a field element there.
So would it make sense to, instead of 2, to say that it's the base, and then instead of shift, that you're dividing by base? Or no?
This is what it attempts to do, but this very code, actually, this code doesn't quite work for polynomials. I had to rewrite it. It's not, this very code does not work for polynomials. Explain to you the algorithm for polynomials. This code doesn't work, right? By the way, just to answer, if you go and look here to what Stevin did, wherever Stevin is, see polynomial over real. He didn't do polynomial over integer. He knew that you couldn't do division of polynomial over. He knew about integer, polynomial with integer coefficients, but he knew that you couldn't run the algorithm. Just answering your question. Okay?
Yes.
Did you know there's a bug?
Is that? Where?
Lowercase polynomial.
Yes, there is a bug. Yes, I didn't know there was a bug, yes. Yeah. Well, we need to make C++ case insensitive. That would be yes, yeah. So, thank you.